Lino, quando vuoi, allora, cominciamo.
Sto registrando.
Okay. So, welcome to everyone to this third session of the PRIMO talks. Today, we are very happy to have as speaker Malena Sabaté Landman. Malena is a brilliant and passionate PhD student at the Center for Doctoral Training in Statistical and Applied Mathematics at the University of Bath. And she's actually about to finish to get her PhD degree. Her studies mainly concern the design of regularization methods for large-scale ill-pose inverse problems in discrete settings. And I think that we should have a nice taste of what she's doing and what she's done recently. So please, Malena, you can share your screen.
All right. Can you see it well?
Yes, yes.
Okay, good. So yeah, thank you very much. Thank you very much for coming. Sorry to the organizers for sending such a bad typeset abstract, but thank you very much for coming anyway. What I'm going to talk about today is it was a work I did last year when I was visiting Jim Nagy in Atlanta, in Emory University. And I'm going to talk about iteratively reweighted flexible curl methods for sparse reconstruction. So I'm sure like a lot of you will be very familiar with the topics I'm discussing today. And hopefully there's some things that you might find interesting. If you want to stop me at any time, ask questions, I would be very welcome. Right, so this is the general setting of my talk. I'm just going to try to find a sparse solution, I said, of a linear discrete ill-pose problem. Here I'm assuming that I know the forward operator. I usually just work with a discretized version of the problem, but it's good to keep in mind where it comes from. So I think it usually comes, or it can typically come from a suitable discretization of the Fredholm integral of the first kind. I will assume that the process is known, so the matrix that involves this problem is known. And I have some sort of measured output that I also know. And usually this output will be corrupted by some kind of noise. So there's a lot of examples of this. I'm very interested in imaging, so I mainly talk about two examples in imaging. The first one is image deblurring. So if I have a PSF or a function that models how one single point, so how one single pixel on an image is spread across the neighboring pixels. So I know I have that information and I have an exact image that was going to be blurred by this PSF. I can think about it as a convolution. So in this case, the kernel just depends on the distance between these two variables. So I can think that this PSF here is applied to each of the pixels of this image. Like in the sense that each pixel goes moved around in this way that the PSF is explaining. And then I have some noise. I usually assume that I do know some things about this noise. For example, I might know the distribution of the noise, of the level of the noise, and I obtain some available blurred image. And my task, or what I want to do, is to go back and find where it came from. Another example that you might also be very familiar with is tomography reconstruction. If in this case, we can think that this is the image we want to reconstruct. This is the famous Sheb-Logan phantom. This image, by the way, really sorry, I forgot to cite it. I will add it in the slides afterwards. But from the Finnish group, they have some amazing,
io sono silenziata. Non è che vuoi...
anyway, some very, very explanatory images that explain how tomography is done. So this is the measuring process. Basically, I have a ray that leaves this red dot here and moves forward to the right, going across this phantom here. And we measure here the intensity that's the result after some absorption has happened through this image. So again, I have some exact image that I want to reconstruct. This is just a description or some schematic way of explaining the measuring process. I have some noise that's been added, and this is the resulting figure that I obtained, that's the measurement, which is also called a Synogram. So you can see, for example, like this line in the middle of the image can be measured by a lot of rays that go like parallel. So like, for example, like this one. So they go all this way around, and then they'll be measured, and like they would be recorded, and you could see that that would correspond to a column of this matrix. And then what you typically would do is they would rotate this phantom some certain degrees, and then you would do that again, and then you would obtain another column of this matrix. So yeah, these are a couple of examples of where these images or these problems can appear. And now I will focus on Krylov methods to solve this kind of problems. And I will, focus on these iteratively weighted flexible Krylov methods that I have been working on. So in general, what's a Krylov subspace? Well, a Krylov subspace is just a space that has this specific form here. So if I have a vector D and a matrix C, I will construct this space by just taking my vector D and then multiplying the matrix by this vector k minus 1 times, and then I would get a space of dimension k. The thing is, like, you want a space that spans this, so it will not always be done in this specific way. You will usually typically add some orthogonalization of the vectors to have a good basis. And the Krylov subspace method is based on finding a solution that belongs to this space, and where the optimality conditions are given by the fact that the residual is orthogonal to another Krylov subspace. In particular, I'm very interested in GMRes and LSQR. And those are, like, I would say, the most typical examples of Krylov subspaces. And they have one particularity that makes them similar, which is that this residual, like the space where we're like trying to find, or like that we're using for the optimality conditions, is the space where of the solution multiplied by the matrix A. So this specific property makes it very simple to reformulate this Krylov subspace method as a minimal residual method. So you will want to find a solution that belongs to this Krylov subspace, minimizing the norm of this residual. So yeah, GMRes and LSQR, the main difference they have is that LSQR works also with the transpose of A. So these are really good methods for really large scale problems, especially with A is really, well, because it's really big, you usually cannot really access it. And you might, for example, just have access to matrix vector products with A or A transpose in the case of LSQR. If A is square and it's, I mean, you'd maybe using GMRes, like, would be suitable for some specific cases. If the matrix is highly non-normal or it's not square, then you'd have to go for something like LSQR, where this is like now a square matrix. So both GMRes and LSQR are regularization methods. And why are they regularization methods? Well, they have a phenomena called semi-convergence. So if you plot the relative errors, as you can see here, and the relative residuals through the iterations for both methods, it's just LSQR, but GMRes would typically perform similarly. You can see that at the beginning, the relative errors and the relative residuals decrease. So again, the relative residuals is just a way of, it's related to the optimality conditions we had before, and I explained earlier. So we are expecting the relative residuals to keep on decreasing, but we can see at the beginning of the iterations, the relative errors also decrease. They keep decreasing, so everything is going fine. But at some point, even if the relative residuals keep decreasing, so in principle, we're doing a good job, we're still minimizing the residual, there's something going on here. So the relative errors start to increase. So if you want to use this as a regularization method, you should be able to tell when to stop. So the point in which you stop, the number of iterations at which you stop, would be your regularization parameter or your regularization criteria. And your method would really depend on this point at which you stop. again, as I said, the L2lp methods are good regularizers, and the two main points why we say that is because they mimic the TSVD if you stop the iterations at some point, or on some point like they mimic the SVD. So that comes from the fact that the projected problem starts approximating better and better the singular values and the singular value decomposition of the full dimensional problem. Another good thing that they provide is that for a small m, the L2lp subspace method start increasing less, and that the way that works is that, for example, for SQR, we were using this L2lp subspace here, and after not that many iterations, we start seeing that this becomes a transpose A invariant. So most of the information of the problem is, like, heuristically, I would say that most of the information of the problem is revealed at the first iterations. So we converge relatively quickly. What happens is because these methods rely a lot on these stopping criteria. You know, if we don't stop early enough, the relative errors can start increasing again. This method is not always very reliable, and sometimes it's used in combination with some direct regularization method, for example, Tikhonov regularization. So I will focus in this particular example. So if we want to solve, so this again applies both for GMRES and SQR, a least squares problem of this kind. So we have the least squares problem, and we're also adding some Tikhonov regularization. If you want to recover the case in which this doesn't have Tikhonov regularization, just set lambda to be 0. By the way, lambda has to be non-negative. L2lp subspace methods are mainly based on updating a partial decomposition of A at each iteration. So the main point, really, like the key point of a L2lp subspace method is being able to update a decomposition of this kind. So basically, we have A times some matrix, and then this is equal to another matrix, which is orthogonal, times a smaller dimensional matrix, which sometimes has also very nice structure, but like fundamentally, the point is that is definitely smaller than the initial dimension of the problem, which is n times n. Now, so what are these matrices? So, well, what we're most interested in is in this matrix VK. So the columns of this matrix VK will span the L2lp subspace we were interested about. So that will depend on the choice of LSQR or GMRES. And at each iteration, what we will do is we will say, well, if X belongs to the L2lp subspace and the columns of VK are spanning this space, that means that we can write xk as a linear combination of these columns. So once you have that, you just have to go and substitute this expression of x into the original system, into the original problem, like both here and here, and then you obtain something that looks like that. And then you use the partial decomposition that you had built in that same iteration to project this least squares problem. Because in this case, I will consider that VK has orthogonal columns, in principle has orthogonal columns, I can also project this Tikhonov regularization term. So what I end up is with like a very, very small problem to solve. So there's something I want you to realize in this particular example. So the thing is that you can, so I was telling you about this idea of adding Tikhonov regularization to a L2lp solver, but it doesn't really matter which way you go. So you can either solve with a L2lp method a Tikhonov problem, or you can apply a Tikhonov problem and then at each of the steps add some regularization term to the projected problem. So what I mean basically is that first regularizing, so that would be this case. So I start with a problem that it's like belonging to, it's like a full dimensional problem. So X belongs to Rn, A is huge. It is a Tikhonov problem. And then I can project it using a L2lp subspace method. And then I obtain I have to solve a projected problem of this form where the columns of decay are orthogonal, so they can be dropped in the norm. And I can recover X in this way. Or I could go completely the other way. So what I could do is I start with my Kirchhoff subspace method. And I think, oh, well, maybe through the iterations, they will start becoming ill-posed at some point. So what I want to do is I want to stabilize these iterations by adding some Tikhonov regularization at each of the projected steps. So I do this, right? Now you see that like here in the regularization term, this VK doesn't even appear, because the way I'm thinking about this problem is thinking that I have this problem that I have projected, and I want to regularize this problem. So I'm applying regularization to these coefficients here straight away. And again, as I said before, in this case, those two things are completely interchangeable. They are equivalent if I fix my regularization parameter. And they can be projected and solved in a small dimension. So now I will go to the topic I'm actually interested in. So this is L2lp regularization. You probably know that this is usually related to recovering a sparse solution. Why? Well, so I still have my fit to data term. It's a 2 norm. Well, if you know a bit about it, you know that just basically means that I'm assuming that the noise that is corrupting my measurements is Gaussian white noise. And then I have this regularization term that concerns my matrix X, my image X. So imagine X is very sparse. So sorry, this P should be small. So I'm usually considering P to be 1, or maybe even smaller than 1, if I'm a bit brave, although that would just lead to a non-convex problem. So I might get problems with that. So just think, for example, that this, instead of being 1, now is 0, right? It's like the 0 quasi-norm. So I'm basically just counting how many pixels are non-zero in this image. So yeah, of course, if my image was very sparse, that number would be very small. So that would be good, like a big number would be penalized. But again, if I would use the 0 quasi-norm, that would be an NP-hard problem. So of course, we cannot deal with that. So we relax the problem a bit. If we don't relax enough, the problem is also non-convex. So we'll just like get to the point where like P is equal to 1 to be sure. The trick I will use here, which is not new, it's been used for a while, is been used in the literature with people that works with iteratively weighted norms or iteratively weighted least squares, which is basically starting from this point where I just rewrite this P norm as a weighted 2 norm. It's a weighted 2 norm, but it's not a linear term anymore, right? Because these weights depend on my solution X. And they're defined in this way. So if you look at this expression, you will definitely tell me, well, you know, you have a problem here because you're telling me that you want a solution that is sparse, so a solution that has a lot of zeros. But if this guy has zeros in its component and P is small, like smaller than 2, then I'll have divisions by 0, and that doesn't sound great. In other words, I'm basically saying that this is not differentiable at 0, and like we're really interested, or like on the 0, like on the neighboring, the neighborhood of 0. Sorry. So there's something that has to be changed here. So the way we deal with it is that we use some smooth version of the same norm. So instead of saying, okay, this P norm is equal to this weight, we'll say, well, they're roughly similar to some smoothed version of this. For example, say like 1 norm with adding some thresholds in a clever way. So these things are now differentiable at 0. And what we can do now is that we can approximate this problem that we had with the sequence. So what we want to do is that we want to get rid of this thing, this nonlinearity in this term. So what we do is we just take some fixed X and we fix these weights to those specific solutions. So that's been done before as well. For example, in the iteratively weighted norm scheme, what you would do is you would run a whole solver. So let's say, for example, like Krylov method, and you would solve the first problem. So you would solve a problem of this kind, and then you would obtain a new solution. And then with this solution, you would update your weights, and then you'd have a new problem that you would like solve completely again. And you would keep on doing that, which works really well and has some really nice convergence proofs, but it gets very expensive because you have an inner-outer scheme. So another way of just looking at this problem, because now this is like just square and it's invertible, we can say, well, why don't we just change variables? We just change this general Tikhonov form into a standard Tikhonov form. That looks great. And also now my weights have become some right preconditioner for my problem. So that's a completely different setting. And we can exploit that. And the way we will exploit it is using something called flexible Krylov subspaces. So flexible Krylov subspaces for problems of this kind have the advantage of being able to incorporate this variable preconditioning. So, sorry, I didn't say that slowly enough, sorry. But what I meant is that if here, instead of doing this inner-outer scheme and solving this problem fully at each iteration, we just update these weights every time we have a new solution. So really at each of the iterations. So we run an iteration of our like flexible solver. We obtain a solution, then we immediately update the weights, and then we perform another iteration. We obtain another solution. We immediately update the weights. Then these weights here will be, well, dependent on the iteration for sure. So we need to resource to a flexible Krylov subspace. So we have a problem of this kind. So it's very similar to the setting we had before when we didn't have any preconditioning. We want to expand a Krylov subspace, but now it'll be a bit of a weird one. So like just remember, these can be moved here as a preconditioner on the right of A. And then the span, the space that we're interested about is spanned by some vectors, which would, you could make a parallelism with the one we had before, but now they are pre-multiplied by these preconditioners. And sorry, there's a typo here. So this is not P, this should just be this Q here. So in GMDRES, because we're just using A at each iteration, we're just taking products of A, we'll just have one times this preconditioner. And in LSQR, because we're multiplying by A and A transpose, this Q will have to be a 2. But those are just like, well, to my understanding, this is like technical details. What I'm most interested about is to showing you how these weights are now affecting the space in which we're finding the solution. So now we want a solution that belongs to this space that is spanned by the columns of ZK. And these columns of ZK have the direct influence of these weighting matrices that come from the regularization term. So basically, we're just thinking that we're modifying this Krylov subspace to incorporate information about the sparsity of the solution. Moreover, the one really good thing about flexible Krylov subspaces is that if I didn't tell you in advance which matrix I'm using to precondition, and I was just giving you, the actions of these matrices on vectors, you could not in principle tell that this is a, an iteratively changing, like a preconditioner that changes at iteration. So at this thing is still a Krylov subspace. You just don't know which is the preconditioner that you're using, and you can just build it a posteriori after you've stopped your iterations. But again, the main idea of a flexible Krylov subspace is very similar to the idea of a Krylov subspace. So basically, you're just updating a partial decomposition of A that has this form. So now we'll usually see that like H gets a bit more complicated and the structure is not as simple as in the case of the non-flexible Krylov subspaces. But again, it's a very small problem, so we can in principle solve it. As well, I'm thinking that UK has orthogonal columns, but now ZK doesn't have orthogonal columns anymore. Because if I think about the V's being orthogonal to each other, well, we still have these guys multiplying them in front, which mess up the orthogonality of this basis. So now we want to consider X to be in this space. So again, we do the same thing that we did before. We just write X as a linear combination of the columns of Z, and then we solve a projected least squares problem. So again, we just take this expression for X, we go to the initial problem, we substitute it, and we obtain something of that looks like that. And we can again project the least square problem, but it's not clear what's going on here because this guy is not orthogonal anymore. So it's really not clear how we can deal with this regularization term. And going back to what I was telling you before about being able to regularize first and then project, or being able to project first and then regularize, well, this doesn't hold anymore for flexible Kirchhoff subspaces. And that makes a difference. So in a similar fashion to what I showed you before, if I just start with the least squares problem, I can add some regularization, some Tikhonov term, and then I can project it using some flexible Kirchhoff subspace, and I get something of this kind. But again, like I will be able to project this, but the only way I'll have to project this, which sorry, I should maybe have said, is using some QR factorization of this matrix here, which is anyway cheap. So what I'm claiming is not that this guy gets hard. Like you can still solve it in a cheap way, but what I'm saying is that you cannot just get rid of this matrix as you did in the non-flexible case. So that would be the other version where you first project. So you start with projected problem and then you try to regularize. And now what I'm regularizing is the projected problem. So I'm just adding a regularization term that concerns this y here, or this vector y. And now these two guys are not the same. So in the literature, like there were a lot of there were like some papers that went this way. That's because in the non-flexible case is typically preferred. You have like a clearer, like cheaper, easier expression of the regularization scheme, which has some advantages. But this branch here had not been explored before. And one of the problems they had with flexible Kirchhoff methods is that they couldn't really get a convergence proof. And the reason is basically, I think, as far as I understand this problem, is in this diagram. So if you were going this way and you wanted to prove convergence, like you wouldn't really know where this guy is converging to, because this regularization term doesn't have an easy kind of an easy translation in the full dimensional problem, so before projection. So yeah, what I did was go this way, basically. So we could like prove convergence of our iteratively weighted flexible GM-Bress or iteratively weighted flexible LSQR to this smoothed version of an L2lp norm. So I'll show you some examples where you can see how this actually performs. So these examples are part of some different toolboxes. You can find them, for example, in the IR tools toolbox. In this case, we have this. I don't know if you can actually see it, but I promise this is not an empty picture. It has some pixels that are non-zero, so it's like a very sparse image. It's just some stars in some purple sky. And we have some variant blur. So we have divided the pixels in 25 regions, and then we have applied some kind of locally different blurring operator to each of these sections. And we have added some Gaussian noise of this level. And we obtain some blurry, noisy measurement of this kind. So we use our algorithm to recover the solution. We obtain relative error plots of this kind. So let me guide you through this. So this is the relative error norm of these different algorithms through the iterations. So this is the algorithm that we're proposing. In this case, is iteratively weighted flexible GM-Bress. So you can see that the error decays very fast and it stays very low. This one that keeps going up and down is the one I was telling you about at some point that had an inner-outer scheme. So you solve one problem fully, then you update your weights using the previously computed approximation of the solution, you solve that second problem fully, and then you can see that this is like the first time you solve the problem. You build another problem, you solve it, and then you keep going like that. So that's, you couldn't expect to reach a better error norm than this method, but you can see that our method gets to the same error norm very quickly. And there's like a couple of other first order methods. This is a comparison, so I just like use Vista, gets the same place, but in this case not as fast. Sparse does not so well. And yeah, I've also compared it to other methods based on Krylov subspaces. So again, you can compare ours with other methods that have been done. Some of them are more general, can like solve a variety of things. This one was like quite tailored to this specific problem, and you can see that it works quite well and it stabilizes in the right way. In particular, I want to pay attention to this pink line. So this corresponds to the opposite approach. So in our case, we first decide to project, we first regularize and then project the problem. This corresponds to the opposite. So we like project it first and then regularizing. And then you can see that you obtain different things. And in particular, now we're just like looking at, or I'll be talking about methods that are just based on Krylov methods. This is just a plot to show the residuals. I haven't said it before, but one of the strengths of our method is that you can still choose the regression parameter at each iteration, and we use it. We solve it. And we decided using the discrepancy principle. So we're basically forcing this line, which is the relative residual, to stay at the noise level. So this is just like a sanity check. The algorithms are doing what we're expecting them to do. And this is what I wanted you to show very quickly, because I think I'm running out of time. So this is a history of the regulation parameters at each iteration. So we really choose the parameter at each iteration for different methods. And again, I'm mainly comparing our method, which is the blue line, with the pink one, which is very similar, but fundamentally different in the way it was built. And we can see that the regularization that is picked is very different, and that's just another thing, or just another proof that we're actually solving different problems. So it makes sense that our method converges to the original full dimensional solution, whereas this one doesn't. We did like a variety of other tests. We can try for different P's. P is equal to 2 is just normal Tikhonov of regularization. P equal to 1 is the most used one, because is the convex better approximation to the zero, like quasi norm. But you can try different other things, and you can see, because this is a very sparse solution, smaller norms are better, basically. We can try other examples. We can still the blurring experiments. In some cases, because the blur is very non-normal, the matrix associated with the blur is non-normal, we might decide to use methods related to LSQR or FLSQR instead of GMRES of GMRES. I won't talk too much about these plots, because they mainly show something very similar to what we saw before. In the previous one, I just like showing you other examples. We can also apply it to tomography reconstruction, and I will get something similar. So we start with some image that is sparse in a sense, and then we take the Synogram of it. We can obtain, again, similar plots. I like to have like some good, fast, reliable convergence. So as a summary, I'm just presented 2 new algorithms to compute sparse solutions for large-scale Z-plus problems. They're both based on constructing a sequence of quadratic problems, approximating the L2lp Regularization scheme. Again, not new, this is like very used. We partially solved each of the subproblems of this sequence, which is, again, already been done, but it seems to be a very good, very fast way of solving this kind of problems. And what is different in our case, that we're using a flexible Krylov method, so we can prove that we're still working with a flexible Krylov subspace, which is a Krylov subspace. So we have some properties, we know some properties about the space, which are interesting for reliability and to be able to study what's going on in the space where the solution lies. And these algorithms are built upon a solid theoretical justification, so the way we build them allow us to have some convergence proof for the results. So yeah, some final remarks. Well, during my PhD, I've been mainly working on L2lp methods and Tikhonov regularization combined in different ways, especially using flexible L2lp methods, not always Tikhonov regularization, actually approximating some other advanced regularization terms, which can be incorporated thanks to the flexibility of flexible L2lp methods. So that's mainly my area of research, and I hope you enjoyed the talk. I'm not going to have any questions.
Thank you, Malena. It was really interesting, and you've been clear through all of your slides. So does anyone have questions or remarks or comments, something to ask, comment?
I have one. Actually, I have just one with actually two curiosities. One, if you go back at, well, whatever slides you have with the Tikhonov one, you always like use the Tikhonov in standard form.
Yes.
Like is it possible to extend this approach for like, yeah, here, perfect.
Yeah.
So you have your WK, which is your non-stationary preconditioner. Is it possible to have like a, let's say, a gradient operator, a differential operator in front of the X?
Yes. But it gets nasty. so I do actually have a paper where we actually try to solve TV regularization. So basically you have a gradient operator in front of X, and you can actually do it, but it gets, more expensive than you would like to. So when you transform into standard form to obtain the preconditioners of your basis, you end up having to solve something that it doesn't look that nice. Because even if it has like a nice structure, it doesn't, like the way you have to transform the problem to make sure they are both equivalent. So you have to do the A-weighted pseudo inverse of that guy, and that ends up being relatively costly.
Yeah,
so you can do it and it works, but again, you have this bottleneck on how you invert these guys.
And the other question is, I've been playing with flexible, generalized L2lp subspaces, not flexible.
Yep.
And there what ends up being, but it's also true in standard L2lp subspaces, that after a while, I mean, you don't really need to enlarge the space. I mean, it doesn't give you any more information. Can you do the same here, or like saying, okay, I don't want to enlarge my space for, I don't know, a couple of iteration, or after, I don't know, 10 iteration, I'm bored of enlarging the space and just stop? Or do you need, because here you have the precondition inside the space, so that might give
so what do
issue.
you mean? Do you mean to update your?
I mean, if let's say that I'm ignorant as I am, I wouldn't use, like, I don't know how flexible LSQR works, and I just use LSQR.
Yep.
So I construct my space, AVK, and then I use the precondition at each iteration. Who cares? Like, I just throw it in there, and whatever happens, happens. I mean, at least with LSQR, if you, after like a dozen iteration, as you said it actually pretty well. It's like, the space become a transposase invariant. That's what you said exactly. So does it happen the same thing here, that the space at some point it's always the same and you don't have anything interesting?
Yeah, of course. Yeah. I mean, the point is that now you are allowed to enlarge the space farther than. So when you have some extra regularization and you combine Kirchhoff subspaces and Tikhonov regularization, you can keep on going for a bit, but you have to stop after a while. You don't want to just keep on going. So it's important to have a good stopping criteria to avoid too much work. But yeah, I mean, you can like see it as well. Okay, I don't have any result plots. Well, I mean, you're like fixing them at the thing. But like, if you didn't fix it with the regularization, you'd see like it still stabilizes at some level.
Okay, just then I stop, I swear.
No,
what is GKSPQ?
Yeah, that's your method.
Ah, okay.
The method you've used.
Okay.
I mean, not just yours, but
yeah, no. If only.
Yeah,
But no,
sorry,
of course
like
it's
all the
not.
details are in the paper.
Yeah, no, of course. Okay, thank you very much.
Welcome.
Any more questions? If not, I would like to ask, you were mentioning the stopping criteria, no? I mean, the fact that you may have a good stopping criteria to stop to enlarge the space and stop when it is enough. What is the stopping criteria that you're using here, just on the relative change or?
Yeah, so it's basically some relative change. So there's different like things that you can control. So for example, I can't remember exactly which one is which in this case. Should like check it again. But there's things like the sparsity in the solution. You can do some numerical, you compute the numerical sparsity in some way and monitor that and see how that stabilizes. You can, in this case, because we were choosing the regularization parameter adaptively as well, you can also see when that stabilizes. So you basically control different elements that change through the iterations, and then you check for some stabilization.
Okay, thank you. Any more comments? Okay. So if not, I think that we can thank Malena for being here and for giving this talk. And I would also like to advertise again the fact that we want more speakers for the next sessions. So if you want to share with us your research, we will be very glad to hear about that. So that's it. Thank you again for the participation.
Thank you,
Malena.
Thank you.
Bye.